and I'm working on satellite plateaus that will fly in about 8 years now, trying to evaluate how many planets it will find and how good it will see them, characterize them to get their radius, their mass, and their density, to know what they are made of usually. But today I want to talk to you about 10 challenge, technological challenge, and I put astronomy, but not only astronomy, it's also space science, so going to space with satellites and so on. So just technological challenge for understanding everything which is in space. And so please keep in mind that I'm not an expert in all those topics. For the question at the end, please no, no question, really picky. But yeah, it's just things that I think are important. It's not necessarily the most important. Some are already solved, and some are being solved, and some don't have solution yet. So let's start. So yeah, I could also have had a more clickbait title with this. Number 7 will blow your mind, because it will. So the first one is actually mirror on the wall. You probably know that from Snow White, and in Snow White they want, the mirror to tell who is the most beautiful. We use mirror all the time in astronomy for visible light or infrared or UV and things like that, to see stars, planets, galaxy, and things like that. And yes, so the thing is, the more light we have, the more we have information on what we observe. And to get more light, we need bigger mirrors. So this, for example, is already a big mirror. You can see the size of the person here. But that's a small mirror, actually, for astronomy. What we are aiming now is mirror of 40 meters of diameter, really big, or even bigger. And it's a big problem because then they are just too big, so you cannot move them. Or they are too big and they are very thin, they break on their own weight. So how do we solve that? Because we want, the mirror I showed before was this size, like about 10 meters maybe, and we want mirror of this size, or this size, 40 meters. So how we do that is that we break them into segments, which is also a challenge because then you have limitation coming from that. And we can build a mirror like here. You can see this is a mirror of GWST, which is done in small segments, so it can fold and unfold also to go to space, because the rocket has a certain diameter. You cannot put a 10 meter mirror in a 7 meter rocket, for example. And so the second one, the slides are getting more and more weird. This offset going more and more.
That's challenge number 7.
Thank you for that. The second is actually about satellites. When we send satellite in space, space is not a friendly environment. It's very harsh. It's like hell, basically, because you have vacuum, so it's not good for your electronics. You can have very cold. If you are not in the sun, you are at minus hundreds of degrees, and if you are facing the sun, you are at plus 100 degrees. So you need to be able to withstand lots of temperatures. You have radiations also. You might know that you have lots of radiation in space. You also have hell of vibration when you take off from Earth in a rocket. Basically, you are on a control bomb. It's not something really nice, so it's shaking in every direction and so on. You also have lightings in space. You might say, but that's weird because there is nothing in space. And we've thought that actually you have those ball bearings that you might know, and you have some in satellites. And it has been a major cause of failure of satellite recently. What we think is happening is that when you have a solar eruption, you have the same things that happens in a cloud, but between the two different rings, metallic rings, and it creates a lightning which destroys that. So that's one thing. Or you have also asteroids and debris which can cause, this is a solar panel from Hubble, and that's just a meteorite that small that just makes this huge impact. So to withstand that, to avoid to be destroyed with those conditions, we just test a lot. We have redundant electronics and things like that on board satellite. It's a huge testing. Actually, testing is a big part when you build a satellite before to send it to space. Then we have human in space, because when you are in space, you have microgravity, and that has a lot of effect on you. For example, you will lose 3% of your bone mass after 10 days only, and then 1 to 2% per month. So it will cause what is called osteoporosis, which means instead of your bone being like that, they will be like very empty, and when you come back to Earth, they will break very easily. So that's only one of the effects of microgravity. How can we go against that? Is astronauts in space, they have their run to do, and we have special equipment for them to do exercise, and usually they spend 4 hours per day just training for strength, so when they come back on Earth, they don't have so much trouble. Still, even with like 4 or 5 hours of training per day, they have troubles when they come back to Earth, because usually they say they take at least 1 day to get equilibrium okay because of gravity, and just to recover for their muscle strength and so on, it's more like a month to 3 months, depending how much time you spend on the ISS, for example. Then we have space debris. And you hear a lot about ecology here and not polluting the environment and stuff like that. But it's the same in space, because we have a lot of debris. And those things, it's not natural. If you why is this great, and why it was a big challenge is because all those antenna you can see here, it's a field of like 100 antenna. Well, because we are able to do that, we don't need to point the antenna in one direction of the sky to observe one source. We just have them there, and we recombine after the signal of the different antenna on a computer, and we can say, okay, I have a delay between the two antenna if I want to observe this direction. And if I want to observe this direction, I put another delay, and by recombining, we can basically observe all the sky with antennas that are not moving. So, which is, I think, quite cool. Then we have data. That's the one that will blow your mind. We are staying with radio astronomy, and I want to talk about SKA. Remember this name? It means square kilometers array, and SKA is a huge project. It's right now being constructed. We have a demonstrator, and it has just been approved as an international organization, just like the ESO, for example, the European Southern Observatory. And SKA will be, you can see all the antenna here. That's just a view for later. It will be thousands and thousands of antenna in South Africa and Australia. The idea is that, just like I mentioned before, we recombine the signal. Here we recombine the signal of all those small, like 5–10 meters antenna. So we have the equivalent of a 50 kilometers antenna in size. And you can guess that thousands of antenna will produce lots of data, which will be a challenge to actually control and to understand. So how many data do you think it will produce compared to the global internet traffic, current global internet traffic? Do you think it's A 0.1, 1 times the global internet traffic, or so who is for A, basically? No one for A. Who is for B? A few people. C. A bit more. D. Not everyone voted there. Who doesn't know? Actually, so when it's fully operational, each should produce more than 100 times the global internet traffic. And you often say that it's impossible. You often hear that it's impossible to control the internet. Well, just imagine we try to control that many data coming from that. Just for the little story, all those antennas will be linked with fiber optics, and there will be enough fiber optic to go twice around the Earth, even if it's so many things. And so I really encourage you to discover more about SKA, because it's a nice project technologically, scientifically, on a human scale also, because they developed also the things for the country and things like that. So please check SKA. Finally, 3 more. Human in space again, but this time radiation. You know that Elon Musk said that he wanted to send an astronaut to Mars by 2025. I think he can do it, but I don't think he can send an astronaut which is still alive when it arrives on Mars. He can send a dead astronaut. Because the problem is, if you want to go to deep space out of the protection of the Earth's magnetosphere, the ISS, the International Space Station, is inside the protection of the Earth's magnetosphere. When you are out of it, you have a hell of radiations, and if you don't want them, you would need a spaceship with walls that thick of metal, at least. And it's not possible because it's just too heavy. We cannot push it to space. So what would happen is that the radiation would actually break your DNA, so you would not survive the trip. One way we can enable us to do that, but without having so much big walls and still like light starships, is by studying, for example, jellyfish or algae, because some specific jellyfish, algae or so, actually, if you break their DNA, they are able to repair their DNA, not like us humans, and they can withstand like 1,000 times the radiation that would kill us. So we are studying them in the hope to find why they can resist so much to radiation, how they are able to repair their DNA, to maybe get medication from it to give to astronauts that would go to Mars. And so then the astronauts will still have their DNA broken, but they will be able to repair it on the way. Then we have electric propulsion. You all know a rocket, like that. It's big, big engine, very, very powerful. And just imagine now this kind of engine, an electric propulsion engine. The thrust, how much force it's giving, it's basically if you blow on your hand, like that, that's the force it's giving. So you could think pushing the satellite, like a satellite which weighs tons, just by blowing like that on it. Not so efficient compared to the rocket. But it's actually a great idea, and it's now being used. It's the first time it was proposed was in something like 1901. And only like 60 years or 50 years later, we got a first prototype, and now we use them on satellite. Why? Because the rocket is very nice to push very fast, but it cannot last long. The electric propulsion here, it can last for years, because you don't need so much fuel like a rocket. So it's a very, very small push, but you can do it for a very, very long time. So you can, for example, go very far away from the sun thanks to that. And the last one is actually to understand what is called extremophily. Just imagine this pool here. It seems like a nice lagoon thing, but it's really not. That's Yellowstone in the USA, so it's a volcano here, basically. It's water from a volcano. And this is 100 degrees. This has sulfuric acid, a very bad pH, so lots of things that would kill you, you know? And yet, you have bacteria living in there. It's called extremophily. You also have, for example, the tardigrade, which is another one. This is a small, really cute thing. It's called the water bear also sometimes, especially in German, for example. And these things are like 0.1 millimeter to 1 millimeter. You can find them in moss. If you go on a wall where there is moss, you take the moss, put it into water, there is a good chance you have one of those inside. I call them the Wolverine of evolution. Those guys are amazing. They can get only 3% of water, they will survive. They can get 1,000 times the radiation that would kill us, survive to minus 270 degrees for 10 years or more, survive 150 degree boiling water, survive lots of chemicals. Basically, if you try to kill them, you have a very, very hard time. Why are they important to understand is that actually they defy the law of life as we usually define it. Because if I ask you the definition of life, probably none of you will have the same answer. And it's because there is no definition of life, actually. And it's important to understand life as we don't imagine it possible. Because if we want to find life on another planet, for example, we need to be able to imagine life other than how we know it on Earth. So, thank you for your attention.